This tutorial demonstrates a 1D unconstrained optimization. And so this is in one variable. In the last tutorial, we created a function which is 2 sine x minus x squared over 10, and this is what its plot looks like. And as you can see that if we are trying to do any kind of unconstrained optimization on this, we have multiple points where the function has a minima. So for this purpose, we will learn a function called fmin unc, which stands for unconstrained. So this is basically saying find the minimum of the function f, and there is no constraint on it. It's unconstrained. So if you type help fmin unconstrained, you can read this detail about how this function works. This is the simplest way you use this function. You provide the function, which is f in our case, which is the function that we have defined, and then also provide where should it start looking for the minima. And this is our starting point from where it will go. It will follow various methods to get to the minimum value. Now there are some options that you can specify with an options argument, and this basically provides some additional information. Let's say you want to give it you may have the information about the first order derivative of the function. You can provide that through options. Also, if you want it to only run for a certain number of iterations, and then after, if it hasn't found a minimum, you want it to stop, you can provide that information through options as well. And there is an additional output that you can get, a second output argument, which is the value of the function at that x point that it has found. So let's run this function for our case. Let's call these x optimal value and the value of the function, which is f optimal value, and then we run it fmin unc, and what we give to it is f and then a starting point. So in this case, of course, we can see the function. We even know where the minima are. But let's say our starting point is 0. Let's start with the 0, and let's run this. So it has found minus 1.74 as the x optimal, and the value of the function is minus 2.27. So let's see. So if we look at this point, that looks like this is the point it found. If you want to confirm it, you can overplot on this plot by running hold on first, which, if you remember from our previous exercises, this means don't erase this plot. I want to put something else on this plot, and then say plot, and then we want to put XOPT on x-axis and FOPT on y-axis, and you can say that I want to show this as red x. Okay, and you can see it has identified that there's the point it found. Let's do one more test. Let's go back to our code for fmin unconstrained, and let's give it a value of 4. Okay, so we know where it will go roughly. So it found 5.26 and minus 4.47. Let's plot it using the code that we already have, and it clearly is this point. And what happens if we give it 8? Okay, of course you can't see the value here, but let's give it 8, and it found 6.45 into 10 to the power 10 and minus 4.1. So clearly this is a point very far away, and which means the program couldn't find a minimum. It diverged when you see these kind of infinite values, and you can also see some of the errors it may generate. Gradient must be also. This is saying that if you provide gradient, it can be another input, but stop because objective function value is less than or equal to the default value of the object function. different message than what we get before, which I didn't talk about, but before you see that optimization completed. And this is because it actually reached the tolerance value, which can be specified through the options. And in this case, it had to stop because it never got to that point. So this can be an indicative of that your tolerance is too big and too small, so it cannot get to that optimal value, or it can also be an indicator that there is no optimal value and the function is causing in a divergence of your process. So this is how you can apply unconstrained optimization to a 1D problem.